Good morning, children. Welcome back to chemistry class. Today we will be talking about real gas equation. In our previous class, we talked about what is ideal gas and what is real gas. Today we will be discussing that why real gases deviate from ideal behavior. What are the reasons that they can't obey PV equals to nRT equation under all experimental conditions? The reason is there are two faulty aspects of kinetic theory of gases. Two assumptions of kinetic theory of gases are not correct. Which are these two assumptions? The first one, no force of attraction between gaseous particles. If we assume that force of attraction is not present, then how can we liquefy a gas? Without force of attraction between the particles, it's not possible for us to liquefy a gas. Because during liquefaction, particles they come closer to each other, and without force of attraction, this phenomena is not possible. It means this parameter is not correct. Got it? Coming to second assumption. Volume of one molecule is negligible as compared to total volume. While finding the volume, kinetic theory neglects the volume of gaseous particles. This we can neglect if total volume is very large. Suppose we have a big hole. In that, as compared to the volume of that hole, we can neglect the volume of gaseous particles as they are very tiny bodies. But when the total volume is less, if the total volume is very less, we cannot neglect the volume of gaseous particles. So due to these two parameters which are not correct under each condition, the gases they couldn't behave like ideal gas under all set of conditions. Right? So these are the two basic differences between ideal gas and real gas. That ideal gas, no force of attraction. No force of attraction. But in real gases, force of attraction is present. It's present, although very small, but still it is there. Second, the size of particles they neglect it. But here we cannot neglect size of particles. We have to consider this parameter also. Right, children? Now we discuss how these parameters changes this equation. This was given by Van der Waals. That's why we call this real gas equation as Van der Waals gas equation. First, we check about pressure, that what kind of correction is required in pressure. Let us take two gas cylinders. Just assume that this is ideal gas and this one is a real gas. I said just assume because practically there is no ideal gas. All gases are real. But we have to imagine, only then we can compare these two parameters for ideal and real. Ideal situation says there is no force of attraction between the particles. If no force of attraction between the particles, it means particles they freely colloid with the walls of container. With their full energy, they colloid with the walls of container. And we know the pressure of gas is due to collision of particles with the walls of container. So, the pressure applied by ideal gas, take it as Pi. Now, just check for real gas. How the pressure comes for real gases? Again, due to bombardment of particles with the walls of container. But we know in real gases, force of attraction between particles is present. So if we take this particle, it experiences force of attraction from the surrounding particles. When surrounding particles, they are attracting these particles towards itself, right, in this way. It experiences a force of attraction due to these surrounding particles. So, before colliding with the wall of container, this force of attraction needs to be broken. It means some amount of energy is consumed in breaking this force of attraction. With leftover energy, this molecule collides with the walls of container. It means comparatively these bombardments are weak as compared to ideal situation. So if the energy of collision decreases, it means the pressure also decreases. So the situation comes to us is, we can say, the real pressure comes less than ideal pressure. Children, this is clear to you? So, if this pressure is coming lesser than this pressure, it means when we substitute this value in this equation, PV equals to nRT, some correction factor should be added to make this real pressure equals to the ideal pressure. So, when we substitute it here, it is equal to P real plus this is a correction factor, small p. This correction factor given by van der Waals, that is A n square over V square. Here, PR is the real pressure, or you can say observed pressure, experimental pressure, any term you can use. A is a van der Waals constant which tells about attractive forces between gaseous particles, because the decrease of pressure is due to presence of these attractive forces between gaseous particles. So A is directly proportional to force of attraction between gaseous particles. And you know number of mole, and V is the volume. So this is about correction factor in pressure. Now we talk about correction in volume. This is ideal volume. Now we have to relate this ideal volume with real volume. The volume, when we are talking about volume, actually this is available volume. What is the meaning by available volume? Available volume means the volume which is available to the particles for their free movement. So this available volume is equal to the volume of container, minus volume of container minus volume of gaseous particles. This would be the available volume which we have to substitute here. So this would be equal to V minus small v. Small v is the volume of gaseous particles. So when we subtract this volume from the volume of container, we will get the available volume which is available to gaseous particles for their free movement. So now this is ideal volume is equal to V minus small v. So again small v is the correction factor which is given by van der Waals. Value of small v is equal to Nb. N number of moles and B is the correction factor, that is B is termed as co-volume or excluded volume. Co-volume or excluded volume. This B is actually equals to 4 times of volume of particle. Why it is 4 times of volume of particles? Because volume of particle is actually the space which a particle is actually covering. Actually covering means its surrounding place also. This you can imagine or you can understand by taking a simple example. Suppose you are sitting in your classroom. So like 15, 20, 30 chairs are placed. That is the sitting arrangement of an ideal classroom. Now, how much space will you occupy? Is the space only equal to your chair or some space surrounding your chair which you need for free movement? Yes, children. All the chairs cannot be placed touching each other. Some space should be left so that you can freely move. So it means that leftover space around your chair is actually your own area. Same for molecule. That's why we take it 4 times of their own volume. And that volume is 4 by 3 pi r cube. So B is actually 4 times of 4 by 3 pi r cube. For numericals, keep this in your mind. How to calculate the value of B. Right? Now we will be substituting the values in ideal gas equation. So at the place of P, we may write real pressure plus A n square over V square. This is the ideal pressure. At the place of V, we will be writing V minus NB. This is ideal pressure and this is ideal volume equals to nRT. So we talked about A and B, that what they actually mean and how do we check their values. More is the value of A, more is the strength of attractive forces between the gaseous particles, right? So now what are the units of A and B? A is actually the corrected pressure, B actually the corrected volume. So small p, that is corrected pressure, A n square over V square, and this is small v equals to NB. From here, A comes equal to PV square over N square. Now check the units: bar, liter square, per mole square. Correct? So its units are bar, liter square, per mole square. This is the unit of A. Now from here, check the unit of B. B equals to V divided by N. So the unit is liter per mole. This is the unit of B, liter per mole. Compressibility factor Z. Simple meaning of compressibility is ability to compress, that up to what extent you can compress a gas. That is the meaning by compressibility. So the deviation of real gases from ideal behavior can also be expressed in terms of Z. So what is the compressibility factor Z? In terms of Z, we express the deviation of real gases from ideal behavior. Formula of Z is, this is the ratio of V real to V ideal. V real means the volume of real gases, Vi is the volume of ideal gases. Now if the value of Z is less than 1, what does it indicate? Means the real volume comes less as compared to ideal volume. So if real volume is coming lesser than ideal volume, real volume coming less, it means particles are very close to each other. So it indicates that force of attraction is more between the particles, because more force of attraction, only then particles comes very close to each other, and if particles are close to each other, it means the volume of gas comes less. Strong force of attraction indicates easy compression of gaseous particles. So it shows compression is easy. Compression is easy. Yes, children, clear this thing? All these relations which are interlinked with each other means if Z is coming less, it means real volume is less as compared to ideal. Real volume is less means more attractive forces. More attractive forces means easy to compress the gas. Now check the another situation, that if Z comes greater than 1. Z comes greater than 1 means real volume is more as compared to ideal volume. Real volume more means particles are away from each other. If they are away from each other means less force of attraction, or you can say repulsive forces are dominating here. Right? Force of repulsion dominates over attractive forces. And if force of repulsion dominates over attractive forces means difficult to compress. Yes, children, clear this thing also? Now check the third situation. Third situation can be that Z is equal to 1. Equal to 1 means this is ideal gas, because real and ideal volume, they are equal. Only then Z comes equal to 1 when the real volume is equal to ideal volume. And when both are equal means forces of attraction are negligible, and that is the ideal situation. So in ideal situation, Z is equal to 1. For real gases, not equal to 1 can be lesser than 1 or greater than 1. Lesser than 1, attractive forces dominates, easy to compress. Greater than 1, repulsive forces dominates, difficult to compress. Now, this is a graph where we show how compressibility factor changes with pressure. Compressibility factor Z is also expressed as PV upon nRT equals to 1. Because we know for ideal gases PV equals to nRT. So PV upon nRT of course comes equal to 1, that is compressibility factor. Check here, this is the line where Z is 1, that is for ideal gases. And this portion shows negative deviation, where Z is less than 1. Less than 1 means A is dominating factor. A is dominating factor. A, that is attractive forces. Right? The graph which is above this line, that shows positive deviation means Z is more than 1. If Z is more than 1, it means here B is dominating factor. B is dominating factor. B is dominating factor means repulsive interactions dominate. Repulsive interactions, they dominate. One more thing you can check in this graph, that this is the portion where the pressure is very low. So at low pressure, the value of Z is almost equal to 1. It indicates that at low pressure, gases, they behave like ideal gases. But when pressure increases, the deviation starts increasing. So from here, one thing is clear, that for real gases, Z is either less than 1 or more than 1. But for ideal gases, this is always equal to 1, and independent on temperature and pressure. I'm repeating it. For ideal gases, always equals to 1, independent on temperature and pressure. But for real gases, this is not equal to 1 and it depends on temperature and pressure. Clear? This graph is plotted at constant temperature. Here we have shown only the variation with pressure. Clear, children, this thing? That for real gases not equal to 1 and it do depend on temperature and pressure. So next point which we need to discuss about compressibility factor is this, that as its one formula is PV upon nRT. So here question comes to our mind is, in this case these pressure and volume, are they ideal or they real? Simply we can check this by using this formula. We know one formula, Z is equal to ratio of real volume to that of ideal volume. Now substitute the value of ideal volume from the ideal gas equation. Ideal gas equation is PV equals to nRT. So V ideal equals to nRT divided by PID. When we substitute this value here in this formula, we will be getting Z equals to V real divided by V ideal, that is nRT over P ideal, or this is equal to P ideal into V real divided by nRT. So children, this is clear that in the formula of compressibility factor Z, the pressure is ideal pressure but volume is real volume. Understood? Now we need to check that what happens when we take low pressure and high temperature. Just write van der Waals gas equation or real gas equation. That is P plus A n square over V square into V minus NB equals to NR. Now we check how these conditions affects this equation. Low pressure means volume is high. Yes, na? Low pressure. So what happens here? Volume is high. And when total volume is very large, then as compared to total volume, we can neglect the volume of particle. Remember this condition? Because we cannot neglect the volume of particles is total volume is very less. But in this case, when we decrease the pressure, volume will increase. Lesser is pressure, more would be the volume. So when total volume increases, we can neglect the volume of particles. So if we neglect the volume of particle, it means this term can be neglected. We can neglect this term. Correction factor is not required. Coming to second situation. When the temperature is high. This was one condition. Second condition, high temperature. And when temperature is high, attractive forces starts decreasing. Now, attractive forces, they starts decreasing. Means we can neglect the force of attraction. This factor we can also neglect. So at high temperature, force of attraction becomes negligible. At high volume, the molecules volume becomes negligible. Means these two correction factors we can neglect. And when we neglect this correction factor, what is left with us? That is PV equals to nRT. That is ideal gas equation. And initially this was the real gas equation. So hence it is proved that at low pressure and high temperature, a real gas starts behaving like a ideal gas. Clear this point? I am repeating, at low pressure and high temperature, a real gas starts behaving like a ideal gas. Now our next definition is boil temperature or boil point. What is boil temperature? Boil temperature is the temperature at which a real gas obey ideal gas equation, or we can say all gas laws. Ideal gas equation over an appreciable range of pressure. So the definition of boil temperature is, this is the temperature at which a gas starts behaving like an ideal gas over an appreciable range of pressure. This temperature is termed as boil temperature. Now what happens at this temperature? And below this temperature and above this temperature, what happens? If the temperature is more than Boyle's temperature, right? If the temperature is more than Boyle's temperature, TB I am writing for Boyle temperature, then the gases show positive deviation. Positive deviation means Z is more than 1. Understood, children? Above Boyle temperature, gases show positive deviation. Positive deviation means Z is greater than 1. And if the situation is opposite to this, second situation, that is, if the temperature is less than Boyle's temperature, less than Boyle's temperature, in this case, Z is less than 1, that is, gases show negative deviation. Now what happens at Boyle's temperature? At Boyle's temperature, the attractive and repulsive interactions between gaseous particles, they comes at a balanced stage, right? Because what is the cause of deviation? Either attractive forces dominates or repulsive forces dominates. In that case, they show either positive deviation or negative deviation. But no deviation means there is a perfect balance between attractive and repulsive interactions. At that stage, a gas starts behaving like ideal gas. And that temperature is termed as Boyle's temperature. And Boyle's temperature depends on the nature of gas. It is different for different gases. With this concept of ideal gases, real gases is complete. Revise it so that all the concepts becomes clear to you.